Check 1, 2. Okay, I'm doing a last call on the snacks, and then we're going to start going here. That was the last call. Wow, okay. All right, that was quick. Well, thank you all for coming. It's a great pleasure and honor to welcome Nikta Fakhri from MIT here today. She's an associate professor at MIT, did her undergrad actually in chemical engineering at Sharif University in Iran, then moved on to do a PhD at Rice University in the group of Matteo Pasquali, also chemical engineering, and then went to Germany, Göttingen. Everyone doing quantum mechanics should know Göttingen because that's an important place. So I stayed there for a couple of years, now is fluent in German, and then came back to join MIT and is now associate professor since last year. She does amazing work. I mean, some people, the term often is a rising star. No, she is already a star now in active matter, soft matter research, especially. She has numerous accolades. She actually got a Sloan Fellowship that I should mention, an NSF Career Award, and then last year an early career award for soft matter research from the American Physical Society. So she's doing amazing work on active matter, living systems, and non-equilibrium. And we're looking forward to your talk. Without further ado, the floor is yours.
Okay. First of all, thank you, Matthias, for inviting me and also for the very kind introduction. I had a great time chatting with everyone throughout the day, and I'm excited to share with you how my group has been pushing the boundaries of non-equilibrium physics in living systems. And I'm a big fan of M.C. Escher, so hopefully by the end of this talk it becomes clear why I have chosen this particular graphics. So let me first give you an overview of what we're excited about. And like many biophysicists, we are fascinated by the fact that there is something different about being alive, and we would like to know what that is in the same way that we know what it is for a collection of atoms to be solid and for a collection of electrons to be superconducting. Now, when you look around more or less immediately, you can identify things which are alive, and the criteria that we use in making this discrimination between animate and inanimate world has nothing to do with the individual components such as DNA or proteins. Being alive is a macroscopic state, while things like DNA and proteins are the components of the microscopic mechanisms by which this state is generated and maintained. To drive this point home, let me talk about this beautiful video that you see on the slide here. This is taken in my group. So first of all, every time I show this video, there are a few in the audience who immediately remember a very famous chemical reaction. It's a BZ reaction. And what I'm going to argue is that this is actually a living cell, and I'm going to tell you what these reaction diffusion processes are. But what I will argue is that in biological systems, we have patterns with a particular function which they deliver. Now, here what you see is self-organized patterns of signaling proteins that orchestrate a very important process early in development, namely cell division. And of course, the ability to divide is a hallmark of life, at least as we know it. Now, we do not see individual proteins. Note that this is a very large cell. It's about 200 micron in diameter, and protein sizes are on the order of a nanometer. And majority of us may not even know what they are, but we can all appreciate the fact that there are these long wavelength patterns and waves that span the entire surface of this cell. They propagate from one side to the other side. They self-organize from one state to the other state. And this happens while the egg cell is continuously consuming ATP and dissipating energy. And the ultimate goal is for these waves to be able to find the center of the cell so you can get a symmetric cell division to happen. Now, over the past many decades, molecular biology has been very successful in identifying the components as well as microscopic mechanisms. However, we have made less progress in identifying the parameters that are characteristic of this macroscopic state. And let me quote Ernest Everett Just, who is a pioneering biologist, where he says that the direct analysis of the state of being alive must never go below the order of organization which characterizes life. Now, if you think about this statement, this is at the heart of physics. One of the fundamental questions that we ask in physics is not only discovering the underlying laws in the system, but in understanding and explaining the new laws that emerge when many individual components interact. Now, to discover these laws, we do not always keep track of all the electrons and protons. We are looking for important variables, or what we call key degrees of freedom. And once these variables are identified, we combine them into what is called an order parameter, which is the quantification of the emergent phenomena. Now, in equilibrium physics, this concept of order parameter has been very powerful. And as you know, it plays a crucial role in defining a wide range of phenomena. I think a classic example that we are all familiar with is magnetization. Now, asking for the order parameters of the living state is a very hard problem. It's also not a well-defined question. And this is because when equilibrium is given, statistical mechanics frames the behavior and phenomena in terms of energy minimization, because no energy is added or lost. And you can write in Hamiltonian, and you have a Boltzmann distribution that describes the system. But when a system is out of equilibrium by necessity, like the case in living systems, we can no longer follow this energy optimization principle. So the question is, can we identify general principles that can guide us in developing a physics of life or living systems that can reach the same level of predictive power that's the standard in any other area of physics? And this is the challenge that we have set out to address, and this is under the umbrella of active matter physics. And to do so, we develop experimental tools to observe and identify non-equilibrium degrees of freedom in the system. We develop data analysis frameworks to define order parameter fields. And then lastly, we collaborate with my theory colleagues to develop theoretical frameworks which have predictive power. And then obviously with these theoretical frameworks in hand, you can go and design this killer experiment that will teach you something more about the system, and you can go through this loop again. Now, the concepts that we develop are system independent. At least that's our hope. Because that's how we are used to this idea that the frameworks in physics should have a universal nature. But we always, of course, need a model system with rich phenomenology of self-organizing principles to be able to develop these frameworks. I'm going to quote Rob Phillips, who wrote this piece about 100th anniversary of Erwin Schrödinger, where he said that we need hydrogen atoms in biology because just like hydrogen atom was this quintessential test case, which taught us what it means, what the behavior of the nucleus means all the way to a Bose-Einstein condensate, we need the same type of model systems which we can develop the phenomenologies that we are interested in. So we use the O site of a C star. So this is an X cell of C star, which is one of the oldest known developmental biology model systems. And what I really love about this is the fact that multicellular development, as it starts from this single O site, And the fact that it has evolved over the past billion years is truly an accomplishment in the realm of self-organization and information processing. You need to really coordinate these processes in space and time to be able to achieve robust outcomes, such as cell division. So today I'm going to, this slide is a journey in space and time to highlight some of the broken symmetries that we have identified and the emergent phenomena that we have discovered. I'm going to briefly walk you through that. So we're going to start at the smallest scale, intracellular scale. And what we have shown is that fluctuations at the small scale, intracellular scale, encode thermodynamic arrow of time. And we have been developing tools from stochastic thermodynamics and information theory to quantify the amount of the spatiotemporal scales of dissipation in living systems. Because again, the dissipation or time reversal symmetry breaks at the smallest scale. And this arguably is the most important broken symmetry that underlies nonequilibrium systems and living systems in particular. Now, I'm going to go one step up in terms of scale as well as complexity. And what you see here is spatiotemporal symmetry breaking and pattern formation in living systems. And what we have shown is that how biochemical signaling patterns can self-organize, how you can have different modules such as gradients, reaction diffusion, where they work together to actually allow the cell to perform computational operations. For instance, the cell can know what exactly its geometry is. But today I'm going to focus on even a much larger scale. It's at the organismal level. And I'm going to talk about a broken symmetry that I've been very obsessed about over the past couple of years, and that's chiral symmetry breaking. And what I'm going to talk about is my group's recent discovery of odd elasticity, which I will tell you what exactly it is. And what you will see is that in systems where you break time reversal symmetry, and when you have non-reciprocal interactions that defy Newton's third law, you can actually get really interesting material properties as the emergent behavior in these systems. Now, so let me introduce you to the periodic table of the talk. I told you hydrogen atom, but it turns out that this is a much larger table that we can look at this type of behavior. So what you see is a tiny branch of the phylogenetic tree. This is the echinoderm branch, and I'm showing you 3 species here. And echinoderms are these exceptional organisms where they start with a bilaterally symmetric larvae or an embryo, very early stage in development, and then they develop into pentameral adult symmetry at much later times. And the way to think about them, we're going to focus on very early stages in development, so which is basically looking at the oocytes of these organisms. And the way to think about them from a physics perspective is that these are self-propelled chiral particles. So they're actually covered with cilia, which I tell you what they are. They can swim around. They use the cilia beating patterns to swim around. And then they have a corkscrew motion when they swim in fluids. And what the main part of my talk is focusing on this species of starfish, Pteria miniata, or bat star. And what I will show you is that a collection of these embryos, these active particles, they can come together to exhibit an interesting collective behavior, and which we call an active living chiral crystal. And then at the end of, if I have a few minutes at the end, I will focus on another organism that we have added to our repertoire recently. This is a sea urchin species. And there I will show you how first initially you get a behavior that's very much like a crystal formation, but then because these organisms break shape symmetry as well, then you end up getting what looks like an active p-adic liquid crystal. So it's very much like an active nematic, but here now you have something that's triangular, so you have an active triadic type liquid crystal. And what I want to convey in this talk is that a combination of time reversal symmetry breaking, so these are non-equilibrium systems, different mechanisms of chiral symmetry breaking, and as well as this action-reaction symmetry breaking can give rise to fundamentally new material properties and collective behavior at much larger scale. Okay, so this is the star of the show. So we're going to start with one of those eggs that I showed you those beautiful patterns on. So those beautiful patterns you don't see them now because we're switching to a bright field microscope, but those are happening everywhere, and they're responsible for this cell division that happened. You saw that we start with a symmetric cell division, and then this process continues many, many times. And you can see that all of this is happening in this case, which is a fertilization envelope. And at some point, you can see that there's a lot of rearrangements within this fertilization envelope. And especially note that there is seem to be a thicker layer at the outside, and this is a three-dimensional object. And these cells on the outside, they have cilia, which is this hair-like protrusion that comes out of the cells. It beats, and then it's responsible for swimming of these objects. And initially, you saw that they had this chaotic motion. They couldn't decide left or right, but at some point, they break that symmetry, and then they start swimming around. So this is the star of this talk, and these are the particles that I will be talking about. And to give you a bit more context about cilia organization and dynamics, this is a close-up view, a fluorescence microscopy of labeling cilia in the system. So again, these are slightly, as you see, these particles are, I call them particles. I think if it was a biology seminar, I would probably have said embryo, but it's basically the building blocks of the talk. So you can see that it's slightly elongated along an axis of symmetry, which we call anterior-posterior axis. And so you have this almost oblong object. And again, it's a 3D object. And what you can see is that it's covered with this hair-like protrusion. And cilia is this very important organ. It's actually found in many type of cells. And in this particular case, it's responsible for signaling as well as swimming of these objects. And just to give you an idea about the dynamics, let's do a high-speed visualization of the dynamics of this cilia. And this is that red box that we had over there. So now you can see that you have a carpet, a nearly full carpet of this cilia. And one way to think about them is that these are active polymers, and they're beating actively. And you can see this nice beating waveform. And then you can see that a collection of those are creating something that looks like metachronal waves. And in fact, this type of waves are pushing the fluid that's next to them around, and that's basically how these objects can swim. And one thing to note is that these embryos, they swim in a chiral fashion. They break left-right symmetry, and then they swim in a chiral fashion because of the dynamics of this cilia. And this left-right cilia is responsible for left-right symmetry breaking in many organisms, actually including us. So now let's look at the dynamics of one of these from far away. So what I'm first, so that we are all on the same page, in this video, we're looking at the side view of one of them. I have the AP axis labeled, so you see what you're looking at. And then what you can see is that there's a water-air interface that has been labeled. The bottom particles are the ones that are swimming in water, and the top ones are the reflection of this at the water-air interface. And what you can see is that these objects, they can come to the water-air interface, and they can attain a stable configuration such that their AP axis is perpendicular to the water-air interface. And you can see that once they're in this stable configuration, they're actually rotating in a handed manner. They're all rotating the same direction. So that's particularly the particle on the left. Now, if you look at the one on the right, you observe something interesting, which is it comes to the water-air interface, but it has a tilt angle with respect to the water-air interface. Still, it's rotating with respect to its AP axis, but it's also wobbling around that tilt angle. So what you really have is a spin and then this an orbit, and then a spin orbit coupling type behavior. And just to see that better, this is the individual ones that are spinning. All of them are spinning. And then the second populations are the one that you have the precision of the axis of rotation. Now, in the first part of my talk, I'm going to tell you and these are two mechanisms for chiral symmetry breaking. And in the first part of my talk, I'm going to focus on the first mechanism of chiral symmetry breaking, which is basically breaking parity by spinning material constituents. And then in the second part of the talk, I will talk about what kind of material properties emerge when you actually also have this spin-orbit coupling within the system. Okay, so now we have this these objects. What do you do with them? So you can. What we decided to do was to get a large population of these tops or spinning objects and put them together. And we observed this absolutely incredible phenomenon. They say a picture speaks 1,000 words, and this is a video, so you can do the math. Just before I start the video, in the first frame, we're looking at the water-air interface from the top. So each of these round objects is one of these stable configuration embryos that are spinning at the water-air interface. And I also want you to note the timestamp as well as the scale here. This is a behavior that's happening on really large scales, like a millimeter scale. So let me just stop talking and show you the video because it's absolutely amazing. So what you see is basically this spontaneous crystallization of a large assembly of these swimming starfish embryos. And over the course of their natural development, a long population of this can come together to form what we call a living chiral crystal structure. And this structure can persist for very long times. You can see from the timestamp, you can see that it can actually persist for days. And this whole formation and a dissolution of this crystal is an autonomous process. It's entirely controlled by the developmental program within each of these embryos. And again, what you can see is that this is something that's happening on a millimeter scale. Now, one thing to note and to remember is that each of these embryos are spinning in a clockwise fashion. And then what you get is the global chiral symmetry breaking of this structure, and hence the living chiral crystal. So I'm going to then later on take you to the co-rotating frame of this crystal and look at some of the excitations within that. But for now, this is the lab frame, and you see this global symmetry breaking. Now, just to give you a sense of scale, this is our attempt on a shot on iPhone. So you can see that you have, this is a 6-well plate, if it means anything to you. So it's a few centimeters across. And then what you can see is that we have nucleation happening, and then these nuclei start merging together to form the larger crystal. So I'm going to spend a little bit of time and focusing on giving you an intuition about why this happens. So again, this is our side view of our embryos. You can see the AP axis. And what you see on the left is the fluid flow that's generated by the cilia beating around these embryos. And this is done via a technique called particle image velocimetry. And then you look at the basically the maximum intensity projection of all these particles. And you can clearly see that it looks like a dipole around this object. Now you can imagine that when you have one of these stable at the water-air interface and one close to it, they become like attractive particles, so they can attract each other, and then you form what's a nuclei, and then this nucleus can grow, and then and many of them can also merge together, so you end up with something that's nearly a large slab of this living chiral crystal. And then one thing to note is that as the time progresses, you can see that both the shape of the particle is changing with time. It's becoming more and more elongated, But you can also see that the fluid flow that's generated by this is changing its topology. And this indeed is the reason that noise is being introduced in the system. And then this results in first a disordered state, and lastly, a complete dissolution of these living chiral crystals. So I'm going to focus a little bit on the fluid flow around them. So now what you see is from the top, so this object is rotating clockwise, and then you can see the tracer particles that are coming in, and then they're pushed down by the embryo to the third dimension. And in fact, you can capture this radial inflow using a Stokes-led flow below a surface. And a Stokes, basically, it's one of the solutions to the Stokes equation that generically describes the fluid flow around a force-exerting object. And in fact, you can see that that Stokes-led singularity is enough to capture both our experimental and as well as this is the theory. So you can see that there's a very good correspondence between them. So this Stokes-led does two things. One is it stabilizes the AP axis orientation of the embryos near water-air interface. But it does something more important, which is it induces this effective long-range hydrodynamic attraction between the embryos. And now what happens is that when they come together, they're still spinning with respect to each other. So what you can see is that they come close. So you have an attractive force. Of course, you have steric repulsion because these are they attract sterically. But then one thing to note is that as they come together, they start spinning with respect to each other. And this is because there's some of this momentum is being, some of the torque is being, they exchange torque with each other, and some of this momentum is being transferred to the fluid. So what you end up having is not just a traditional, basically, attraction and steric repulsion, but an additional exchange of transverse force and torque, which is actually are not balanced, so they're non-reciprocal type interactions. And this is what I will call microscopic non-reciprocity. So it's a microscopic interaction within the system, which is non-reciprocal. And in a few slides, you will see what is the consequence of having this type of interactions within the system. This is a crystal, so we're going to focus a little bit first on the ground state of this system. And we can look at a number of different order parameters to understand structure and dynamics. I'm going to show you one example of this, which is basically tells you kind of how order-disorder transition happens in the system. And the particular order parameter that I have chosen is orientational order parameter, or psi 6. So this is a bond orientational order parameter. And the magnitude of psi 6 is quantifying the local hexagonal order within the system. And the phase angle is indicating the local bond orientation within the system. And on the left, what you see is the magnitude of psi 6. And on the right, what you see is the phase of psi 6. And what you see is that initially we have a few of these crystal nuclei that come together. And of course, because they come together, they have formed in different locations, they come together, you have a lot of grain boundaries. So the crystal is disordered initially. But because these domains can rotate with respect to each other, after a while you get a nice, nearly defect-free crystal. And then at some point, as you remember, these particles are changing shape as well as the fluid flow. So you're introducing noise in the system, and that's why the system starts becoming less and less ordered, and at some point you get a complete dissolution in the system. And these videos are experimental evolution of the order parameter within your system. And I'm briefly going to show this. So those videos play continuously, so this is easier to see. So this is looking at the distribution of the phase and the magnitude of psi 6. And you can clearly see this order to disorder transition as the system goes through development. Now, of course, the ground state of the crystal like this is interesting, but what we observed was that the excitations in this system is even more interesting. And in particular, one of the questions we were interested in is trying to understand how does the excitations look like in a system that's breaking parity at the individual particle, and the fact that each particle, again, is spinning. And again, I want to remind you that we have a global chiral symmetry breaking, and that's understandable because each particle is rotating with respect to each other. And despite the fact that when they come together, they rotate slower, but still that's preserved and the whole global symmetry is broken. But now let's look at the co-rotating frame of one of these crystals, and we observe this absolutely remarkable phenomenon. And I'm going to play the video. And what you observe is this long-lived chiral shear cycles and strain waves within the system, which is quite unusual, mainly because if you look at the time scale here, this is a type of wave propagation, strain wave propagation within the system that's persisting for hours. And this should come as a total surprise because this is a fluid-embedded crystal, so this is an overdamped system, and the presence of such long-lived oscillations should, again, come as a total surprise. And just to better show you, let's look at the displacement field. We can identify the angle as well as the magnitude of displacement field. And now you can clearly see the nature of this chiral wave propagation within the system much better. And also the fact that this persists for a very long time. And if you're still not surprised, let me remind you about textbook elasticity. So this in standard elasticity, so this is this tensor version of Hooke's law. So in standard elasticity, we derive the entries of this stiffness tensor under a variety of assumptions. And energy conservation has a very important consequence, which is in the case of a two-dimensional isotropic media, it constrains the entries only to two diagonal entries. One is the bulk moduli, and the other one is mu, the shear moduli, the two moduli that we are all familiar with. Now, in 2020, there was this really beautiful work from Vincenzo Vitali's group and co-workers, where they showed that if you remove this energy conservation constraint, one can unravel unexpected mechanical behavior that has previously been overlooked. And this is because by removing this constraint, you can actually get entirely new moduli appearing in the stiffness tensor. And these are off-diagonal components, and hence they call this odd elasticity. And what you can imagine now, what happens is that if you look at the displacement tensor and the stress, the principal components of the stress, what you can see is that now you can couple modes that were previously you were not allowed to couple them. So usually if you push on a material, it will not rotate. But now, because you have this new moduli in the system, if you push on a material, it can rotate. And this is a macroscopic non-reciprocal response within the system. And the origin of this macroscopic non-reciprocal response is the microscopic non-reciprocal interactions that you have at the level of individual particles. And to see this better, one of the consequences of having this a non-reciprocal response is the fact that the system can, under certain excitations, it can actually exhibit this type of oscillatory behavior. And you can, so what we can do is we can look at the four principal components of the displacement gradient tensor. So this is divergence, curl, shear 1, and shear 2. And then what we have plotted here is that we have gone along the boundary of the crystal and plotted the magnitude of this as a function of time. This is called a chymograph. So what you can see is clearly this type of oscillation behavior over time, which is, again, a very long-lived type process. Now, you may ask, what's really unusual about this type of, having this type of response within your system, or this type of oscillations within your system? And to better understand this, what we are going to do is we're going to take two of these components, and we're going to construct a phase space of two of these components, and then look at the trajectories within this phase space. And what we observed was that the trajectories trace out a closed ellipse. And this ellipse indicates the emergence of an autonomous, self-sustaining elastic engine cycle in which the system is converting internal energy to offset dissipative losses, into mechanical work to offset dissipative losses. And in fact, the area that's embedded by these ellipses is the work. And if you look at the signs, and like remember from thermodynamics, if you look at the signs, you will see that this is a positive work, which by convention it means that the system is doing work on the environment. So in other words, you have built an engine. And what I really love about this is that it brings together two things that I absolutely love, which is rigid body mechanics and thermodynamics, so building an odd elastic engine. This is similarly true if you look at the two other components. And what are the bounds on the work and dissipation that's being generated in this system? And my group has been developing tools from stochastic thermodynamics and information theory to be able to bound the amount of work in these systems, or in general in non-equilibrium systems. And one technique is basically to look at the statistical irreversibility of these cycles within the phase space, and then you can put a bound on how much energy is being dissipated within the system. And this is now shown as a heat map. And what you can see is that the system is clearly dissipating a lot of energy when it's excited. But one other thing to note is that you seem to have a lot of localized regions within the crystal itself. And it turns out that these are close to where you have defects within the system. And this is a nice gateway to get to think a little bit about elastostatics within the system. Everything we talked about was dynamics. So let's focus a little bit on the statics. And this is a close-up view of the crystal. And you can see that this system can have different types of defects. You can have, if you look at the orange, the defect that's colored orange, that's actually an embryo that's sitting on its side, and that generates a 7-fold coordination defect. And if you look at the purple one, that's a departing embryo, and that creates a 5-fold coordination defect, vacancy defect. But you can also have bound 5, 7-fold coordinated defects. And this is a technical slide, but I'm very excited about it. So I'm just going to very briefly mention that the strain field around these bound defects actually contain information about the material properties of your crystal. And in fact, you can parameterize the strain field using two angles, and then in a classical case, you have a very simple relation between these two angles that parameterizes the strain field. But then the presence of odd elasticity introduces an additional deformation. And in fact, from that residue, you can get the ratios of odd elastic properties within your system. Again, the theory of this was developed by Vincenzo's group. Okay, so I'm going to now stop here. Everything we talked about was this particular mode of symmetry breaking, which is each individual particle is spinning within the system. And I'm going to now focus on what happens when you have the second mechanism of chiral symmetry breaking, which is, again, to remind you where one of the embryos can come to the water interface, but now they have a tilt with respect to the horizontal vertical angle, and then you have a precision of the embryo along this axis of rotation. And now the question is, what's the consequence of having, looking actually at the third dimension within the system, where now you have this spin-orbit coupling within your system? And the thing that we observed, which allowed us to actually understand that we have another mode of symmetry breaking within the system, was the fact that we not only can have this type of strain oscillations within the system, but you can also get velocity oscillations within the system, which means that the system can actually seem to coordinate over very large distances, and then you get velocity oscillations and coordination over very long distances. And to demonstrate this, I'm going to kind of take a small region within this, and then we're going to look at the population of on the top, you see the population of the embryos that starts oscillating. And in the bottom, we're plotting the mean velocity in the x and y direction. And you clearly see that initially we had just fluctuations. And then at some point, you end up in a second state, which is this oscillatory state. And then now you're going around this cone, which has a very well-defined diameter. And the system stays there. And you can see that now at some point you get the population of the oscillating ones or synchronized one die out, and then you end up in the quiescent state. And this is looking at the global average velocity, but as you can see, we also have this spatial dynamics. And you can see we start with a small region, and this region can grow and then eventually can die out. So you can end up in these two states. And the way we understand this is basically the fact that now each of these embryos, they not only spin, but they can also spin-orbit couple. And then what happens is that then we can no longer just look at the displacement field. We actually have to introduce two additional fields within the system. And one basically to account for the orientational dynamics of the embryos. And the first one would be the tilt angle, which is the theta equation. And the other field would be the azimuthal angle. And I'm not going to go into details of this, but I want to draw your attention to the theta angle. And if you look at this, what you will see is that the way we have, it's a phenomenological model, but the way we have defined this is that the angle, the embryo with respect to angle is bistable, so it can have two states. It can either be in the theta naught state or the theta C state, or basically the theta 0. So it has a bistable, each embryo is a bistable object. And then the equation that you can see is that it's basically bistability in the tilt angle that's propagating. So if you're familiar with population dynamics, it's very much like you have a tilt population that starts growing and expanding into, just like Fisher waves, how they propagate within the system. And again, I'm happy to answer questions about the model itself, but the model has a few key predictions, and then in fact, we can observe those predictions within the system. One is the fact that when the system is in the oscillatory state, you get on average more tilt angle within the system. But the other one is that you can get a coupling, in-phase coupling between the divergence as well as the rotation frequency of individual embryos. And in fact, this is also what we observe, which they're also in phase. Now, okay, this type of interesting, the fact that you have a bistable system and you can observe this spontaneous oscillations. But one of the big questions we wanted to understand was whether we can control this. Actually, can we excite the system? Do we know what proper perturbation we have to introduce to be able to excite the system? And the way we did it is we decided to go use a mechanical perturbation. And what we have done is we have developed a chamber, 3 walls with one piston that you can control either the compression rate, or you can apply some oscillatory compression. Here, what we are going to look at is uniaxial compression. And we can put our crystal within this chamber, and then we can apply different compression rates. And in fact, what we observed was the fact that under certain compression rates, we can excite this type of oscillations within the system. And it turns out that it's actually not all compression rates are equal, as you might imagine. You have a Goldilocks situation here, which is if you go too slow, you're mainly looking at low wave vector deformations, whereas if you go too fast, you're basically creating plastic deformations within the system. And it is really in this region that you get excitation of this long, basically excite the system from one state to the other state. And in fact, the theory can also predict that you can have this unstable band that grows under a certain, and it has a direct relation with the compression strain rate. Now, how much time do I have? Okay, great. So in the few minutes, I'm going to focus on mostly ongoing work, which is basically we've been working on and trying to really understand the result. But this particular one I'm very excited about. And that's the fact that when you have a system like this, it would be amazing to be able to get the dispersion relation from the system, because in particular, we can see that we can get two types of oscillatory behavior from in this system: strain oscillations, or the odd oscillations, or this velocity oscillations by stability within the system. So if we can get the dispersion relation, in fact, we will be able to see whether it's possible we can, in a way, tune the ratios or the contributions of these symmetry breaking, chiral symmetry breakings to the response of the collective at large scale. So this is now, very recently, it's been a possibility. So I will just again, these are still work that we are trying to understand, but we've been collaborating with my colleague, Jorn Dunkel, and we've been developing dynamical mode decomposition techniques to be able to extract the most important modes within the system. And then this is a 9-mode reconstruction, and we can get the large global rotation mode. And as well as what we see is that we get two branches within the system. One is a acoustic branch, so you have an elastic material, so you can get the acoustic branch, and then you can get what looks like an optical branch. It's a dissipation-less flat band. And this is still, we're trying to kind of like put, these are all data-driven, so we're trying to put error bars on and try to really understand each of these branches. But just briefly, again, what we see is that global rotation, which is obviously the dominant one that comes out of it, then we have what looks like a quadratic band. And then finally, we seem to have like a flat band that's the signature of having velocity oscillations within the system. And there are two interesting results which we're trying to further explore, which is in this system, you can look at the imaginary part as well as the real part of the frequencies. And then in an odd material, you have a certain relation between them. And we certainly seem to get that relation, and that actually is a third way to be able to get odd elasticity from the system. But one of the things we really wanted to understand was, okay, if these modes are significant, then we should be able to design an experiment where you can remove the optical band from the system, because that's really only depends on the tilt dynamics. So the experiment we designed was as follows. So what we are going to do is we're going to do the compression rate experiment that we do, but this time we're going to do consecutive compressions. And the way to think about this experiment, or at least our idea, is that every time you compress more the system, you're basically removing the tilt degrees of freedom. So the system has less place to be able to tilt, and that way you can effectively, you should remove that optical flat band from the system. And we have indications that that indeed is the case, but again, hopefully I can show that in another talk. Okay, now I'm going to just quickly show a few last things, which are what this system, which really exemplifies this upward energy transport in active matter, can allow us to start exploring. So this is an example where you can 3D print an object, and then we call this the wheel of time reversal asymmetry. And again, this system exemplifies this upward energy cascade within the system, where you start from a single particle, cilia beating, ATP consumption, and energy dissipation, all the way to the fact that you can get structure, that you can get work out of it. And that's just not there. You can look at the effect of boundary. You can imagine that when you have a system that can exert torque and force on the boundary, you can get interesting melting behavior within the system. This is, I was asked by David Nelson to see if I can put this on curved surfaces and different geometries. So you can now indeed play with concave, convex, flat surfaces, as well as look at the role of geometry within the system. You can actually do active crystallography, so you can remove one of these embryos and replace it with a ferrofluid droplet, where you can actuate and try to really measure not just the ratios of material properties, but put scales on those. And then you can do even better. Everything I showed you was using a system of identical particles, because we can start at the same developmental time, mix them together. But you can do a lot better. You can a lot more. You can actually start mixing particles of different developmental time. And here, what you're doing is basically you can get. Basically, what you're doing is you're changing the strength of non-reciprocal interaction within the system, and you get a broad range of, it's a huge phase diagram that you're trying to explore. You can get phase separation, but you can also get different collective behavior emerging, this is an example where instead of starting from the crystal formation and a living chiral crystal, you actually start from chiral flocking, and then you transition to a chiral crystal state. And if you look at the two order parameters, for instance, the crystalline order as well as the mean polarization, or mean aligned alignment or velocity alignment, what you can see is that the system actually exhibits what's kind of like now is known as a non-reciprocal phase transition, because your order parameter oscillates, and then first it goes through this conic region, and then it goes through a half bifurcation, and then ends up in the static state, which is a crystal state. And I'm going to skip this, but you can kind of show that this is indeed actually a non-reciprocal phase transition. And then the last thing I'm going to show is that, as I mentioned, you actually have a periodic table of these type of particles to play with. You can look at now a species which not only has the same features of being chiral, but it can also break shape symmetry. And this is sea urchin at a later state. And you can see that from the top, you seem to start developing this kind of this, almost like a triangular structure. And then what happens is that this system as well can exhibit collective behavior. This is a very robust behavior. And then here, because of the fact that you have this shape of the particles, you can play with the density. What you end up getting is not a crystal, but rather what seems to behave like an active p-adic liquid crystal. And then, for instance, you can look at the polarization and on and on. And then you can even go further. And this is when the sea urchin embryo starts developing this kind of like structure. It almost looks like a half Eiffel Tower structure. And then you can, it really looks like nature is 3D printing active self-propelled particles for us. And this gives us an opportunity to really think about what kind of phases do we get, what kind of phase transitions do we get, but also gives us ideas about how we can push in this direction of designing soft robotics and collective behavior in different systems. And I'm going to just end where I started by this question of what is life. And I believe that this non-equilibrium, the same approach that we have taken in equilibrium physics and extending it to non-equilibrium physics can give us an opportunity to be able to understand this big question. But what I personally find exciting is the fact that these systems are giving us an opportunity to do new physics. And to learn more about this is an article that I have, perspective article that I've written with my three colleagues, and there we really look at what the future holds for active matter. And with that, this is the work of an amazing group of graduate students, former members, current members, my group, undergraduates, postdoctoral fellows, as well as my theory collaborators across the globe. And I'm happy to take questions.
Thank you so much. Fantastic talk. I'm sure there must be questions. Oh, so many. All right. Like maybe Derek first. And
okay. Thank you.
Have you tried applying rotations to your entire system?
Yes, so we have done all this kind of like, this is a system of 2-year-old, so we've been doing a lot of things, but yes, we've kind of like do the crude version of like putting it on, kind of like try to just rotate the whole thing. We even try to put it on basically apply sound waves going through this. So yeah, this certainly those are things that at some point would be interesting to try to further explore. Yes, yeah.
Did the rotation, does it strengthen or weaken the lattice you see?
We haven't done something that's very quantitative or careful, so I will answer that question maybe, hopefully. Yes, that's sure.
First you, then Kyung-Suk.
Yeah, great talk. I was curious, have you looked at any concentration-dependent effects in terms of, say, defects that arise in the crystal, slower?
Yes. Yeah, and that's a great question. And we started noticing that when we looked at the effect of boundaries, because when you have like crystal can grow to reach all the way the boundary, there you can, depending on the boundary itself, you can actually have defects getting created from the boundary and then kind of propagating all the way in. So there's a lot of interesting things to look at the role of the density and how, mostly density and how it results in interacting with the boundary. When you have a free surface, what happens is that the crystal can just grow and yeah.
Kyung-Suk, him, and then...
Oh, yeah, so very interesting talk. So,
thank you.
In your crystalline state, so do you have any distinct Roton or Maxon states when you have a dispersion relation?
Yeah, the dispersion relation is really a month-old result, so we're really trying to understand whether there are more branches or, because we need to put error bars on everything to be able to say whether these, well, we have a lot of points, and obviously, like you just knowing what the system is, we do think we see like a quadratic branch. There may be 2 branches, so I think the dispersion relation is going to give us a lot of information, but we have to first make sure that all these points have significant statistical significance before we can, but those are what I really hope to be able to kind of like answer. Yes, thank you.
Mm-hmm. Yep.
Thanks for the talk. Just to, I was curious, have you tried extending to systems with more than one type of embryo? So now you have like more than one crystal within the same volume?
Of the same species or different? Yeah, I mean, these are all just anecdotal type experiments we tried. Not a lot. So just we've tried some, but initially when they're very similar in at least shape, you can form like particles of like, you can form like maybe a mixed state, but that's again very anecdotal and yeah, we don't know. Like, I mean, at later stages, I think that's also would be interesting, but we haven't really explored that, I guess, axis.
A quick last question, Brad Morrison.
In phases that have broken time reversal symmetry, is there any evidence for waves of topological origin, like Marchetti and Bode have been tested?
Yes. So this is something that we've also been looking a lot into, but again, these are like finite size experimental systems. So just to kind of like try to really know whether what we see like has some will probably have some penetration depth or something like this. I think those are things that will certainly be a direction I want to go, but make sure that like it's beyond just a finite size system observation. Yes. But the chiral wave seems to have actually a chiral nature, which makes us think, yes. And maybe the last thing I would say, and when we put them in the boundaries, actually we see that the outer layer is moving much faster. Like so you get a range of different kind of like velocities, and you get vortices. So you get a middle vortex, and then you get small vortices around. So it very much look like kind of maybe, again, I don't want to make too many analogies, but maybe something that's like, related to those, but yes. Sure.
In the interest of time, we should end here because I know some people may want to walk over. So if you have questions, come down. Let's thank the speaker again. Fantastic talk.
Yeah, thank you so much. Thank you so much.